This lesson is on the counting principle of inclusion-exclusion. So the addition rule that we saw earlier only applies to disjoint sets. If sets are not disjoint, then you can still count them using a rule called inclusion-exclusion. So for any two sets A and B, the number of elements in A union B is equal to the number of elements in A plus the number of elements in B minus the number of elements in A intersect B. We'll prove this for two sets. So all the elements that are in A are either elements of B or they aren't. So we can rewrite any set A as A intersect B union A intersect B complement. So this is just rewriting A as the elements in A and B and the elements in A and not in B. And if we take this union with B, then A union B becomes the elements in A and B union the elements in A and not in B union B. So here we're just substituting this above formula for A. So A intersect B union B is just B itself, right? Because this is everything that's in A and B, then we're including everything in B. And since this set on the left already was in B, but it's possibly smaller than B because all these elements also have to be in A, unioning with B just gives you B. And that reduces this formula, so we're going to take the A intersect B, union the B, and just combine that to B. So A union B is equal to everything in A that's not in B unioned with everything that's in B. And these two sets are disjoint because everything that's A and not in B means that the elements are not in B, and this set B means the elements are in B. So if we look at the number of elements in A intersect B complement union B, by the addition rule, since these are disjoint sets, we can just add the elements in both sets. So it's the number of elements in A intersect B complement plus the number of elements in B. And since these two things are equal, this says that the number of elements in A union B is equal to the number of elements in A intersect B complement plus the number of elements in B. Now we're going to once again use the fact that A can be written as two disjoint sets to rewrite this intersection of A and B complement. So A is once again everything in A and B, or A and not in B. And since those two sets are disjoint, we can use the addition rule to say the number of elements in A is the number of elements in A that are in B plus the number of elements in A that aren't in B. And rearranging this just by bringing this, I guess I flipped the equality, but essentially we're just subtracting A intersect B to the other side. So that means the number of elements in A and that aren't in B is equal to the number of elements in A minus the number of elements in A that are in B. So we want to substitute this formula back in up here. So the number of elements in A union B is equal to, and now substituting this, we get the number of elements in A minus A intersect B plus the number of elements in B, which is the inclusion-exclusion formula. So I won't scroll back up to it, but just writing this on one line, the number of elements in A union B is the number in A plus the number in B minus the number in both. We could also extend this to more sets. So if we have three sets, then the number of elements in A union B union C is the number in A plus the number in B plus the number in C minus all the pairs. So minus the number in A and B, minus the number in A and C, minus the number in B and C, then plus the number of elements that are in all three, A union B union C. So you include all the sets by themselves, then you exclude all the pairs of sets, then you include all the triples of sets, and you would exclude all the quadruples and include all the quintuples, you know. So you go 1, 2, 3, 4, 5 with plus and minus, and all possible arrangements whenever you do this generally. And you do that until you run out of sets. So we can't go any more than 3 sets whenever we started with 3 sets. And so you can do this for n sets. So if we have sets a1 through an, we have the index set I equals 1 through n, and for each I inside of I, we can let j sub I be the subsets of cardinality I, meaning j sub 1 is all the 1-point sets, and j sub 2 is all the 2-point sets, and so on. And the number of elements in the union of the AIs is going to be the sum from 1 to n of negative 1 to the I minus 1 times the sum over all subsets, well, all elements j and ji, which are sets because they're sets of cardinality I, of the number of elements in the intersection of j and j of aj, which is a mouthful to say, and we're not going to even try to prove that, but there's a formula for the general inclusion-exclusion formula on n sets. We will, however, do an example. So let's do one for 3 sets, but we're going to use the notation from the general inclusion-exclusion formula to explain what all's going on in that. So let's let A be the set 1, 2, 3, 4, A1, A2 is the set 2, 4, 5, 6, and A3 is the set 4, 5, 7. So our index set is 1, 2, 3 because we have 3 sets. Now J1 is the set of all 1-point subsets. So J1 is the set of 1, the set of 2, and the set of 3. J2 is the set of all 2-point subsets. So it's 1, 2, 1, 3, and 2, 3. And J3 is the set of all 3-point subsets. So it's the set 1, 2, 3. That's as far as we can go because we only have 3 sets. So if we just directly compute the number of elements in this union, so if we take the union of A1, A2, A3 and then find how many points are there, we get all the numbers 1, 2, 3, 4, 5, 6, 7, which has 7 elements in it. So there are 7 elements in the union of all these sets. That is, if we look at the sets above as they're defined, there are 7 distinct points among all the sets. Now let's look at the left-hand side. So applying that equation, the first thing we're going to do is take the sum I equals 1 to 3. So whenever we plug in 1, we get negative 1 to the 1 minus 1, where there was an I. And then the sum over j and j sub I is the sum over j and j sub 1. And then we're going to do the same for each term. So we're going to have I equals 2 and j sub I where I is 2. So we're going to plug in a 2 here and j sub 2 here. And finally for the last one, we plug in the 3 and the exponent and the 3 for the set. Now we can go ahead and compute the negative 1 to whatever power. So negative 1 to the 1 minus 1 is just 1. Negative 1 to the 2 minus 1 is a negative 1, so it's going to be minus this. And negative 1 to the 3 minus 1 is negative 1 squared, or positive 1, so it's plus this. Now we're going to sum over each of the sets. So first we're going to compute this one. That is, we're going to sum over j sub 1. And doing that, we sum over all the 1-point sets, because j1 is the 1-point sets. So we're going to sum over the intersection of j in the set 1 only, plus the sum over j in the set 2 only, plus, sorry, that should be intersection, plus the intersection over j in 3 only, which is, if you just intersect a1 with nothing, it's a1, a2, and a3. So we're going to add up the sizes of each of the sets. In other words, it's the size of a1 plus the size of a2 plus the size of a3, which was a 4-point set, a 4-point set, and a 3-point set. So that gives us 11. Now we're going to compute this middle part. So now we're summing over j2 in particular. And j2 is all the 2-point sets. So we're going to intersect all possible pairs. We're going to sum over 1, 2, 1, 3, and 2, 3. In other words, a1 and a2, a1 and a3, and a2 and a3. And so we're going to intersect each pair. So a1 intersect a2 is the set 1, 2, 3, 4 intersect 2, 4, 5, 6, which is 2, 4. a1 intersect a3 is, so let me underline, A1 intersect A3 is the part we're looking at. It's these two sets, just plugging them in, 1, 2, 3, 4, and 4, 5, 7, and their intersection is just 4. It's the only point they have in common. And then we do the same thing for this 2-point set, which is these two sets, which is 4, 5. And finally we count the number in each of these sets, so it's 2, 1, and 2, which gives us 5. And lastly, we'll compute this part of the sum with j equals 3. So we do this over all 3-point sets, and that's just one possible set, 1, 2, 3. So we're going to put in A1 intersect A2 intersect A3, which is these 3 sets, and their intersection over all the sets is 4. Counting that means there's 1 point in that set. And plugging these values in, so we just computed each of these 3 individually to be 11, 5, and 1. So it's 11 minus 5 plus 1, which does equal 7, and therefore we get the right value. So the number of points we have to choose among are 7. So let's look at one way we could use this. Suppose we know how many elements are in each set and the intersection of each set. So we know A1 has 5 elements, A2 has 7, and A3 has 10. And then A1 and A2 have 4 in common. A1 and A3 have 3 points in common. And A2 and A3 have 5 points in common. And all 3 of the sets have 2 points in common. We want to know how many points are there in A1, A2, and A3 altogether. So for example, if we were to choose a point from A1, A2, or A3, how many possible outcomes could we have? Well, by the inclusion-exclusion formula, we can add the points in each set, subtract the number of points in each of the pairs, and then add the number of points that are in all 3 sets. So since we're given that information, it's 5 plus 7 plus 10, so add the number of points in each set, subtract the number of points in each pair, so minus 4, minus 3, minus 5, and then add the number of points in all 3 sets, so plus 2. And that's where this comes from. So we're going to add the 5, 7, 10, subtract the 4, 3, and 5, and then do plus 2. And this comes out to 12. So there are 12 distinct elements in the sets A1, A2, and A3. So it's a method of counting whenever the sets overlap. If we went back to, for example, the basketball example and the addition lesson, it's kind of like saying one store has 5 colors, one store has 7, and one has 10. But 2 of the stores, A1 and A2, have 4 of the same colors, so they're not really new choices. 2 of the stores in A1 and A3 have 3 of the same colors, and A2 and A3 have 5 of the same colors, and there's even 2 colors that are in all 3 stores. Then we only have 12 different colors to choose from. So let's look at an informal explanation of why this works. So here's a diagram of the sets A and B, and the first thing we're going to do is count all the elements in A. So if we count the elements in A, we're going to count this region here on the left, so everything in here is going to be counted once. And also everything in this middle part is going to be counted once, because A is the red circle, and so we're counting everything inside of A. Now we're going to count also everything inside of B. So counting in A and in B would give us the number of elements in A plus the number of elements in B. So whenever I count B, I would count this region once, but I would also count this middle region once. And it already was counted once, which means that I've now counted this region twice, because I counted it once when I counted A, and I counted it once when I counted B. So we want to subtract that region, because we've counted it twice. So the number in A plus the number of B minus the number in the intersection would now bring this middle part back down to just counting it one time. So we've counted all the elements in here one time, all the elements in here one time, and all the elements in here one time, which is the same as counting all the elements that are in A or B.